should pop up. Oh yeah, now, yeah, perfect. Thank you. Sorry about that. Thank you very much.
Okay.
Yeah. All right.
Good. So then let's go and have this meeting taped.
Okay, so thank you very much for the invitation. We switch into English. And now going to share my screen. I hope it works. We made a test and it should be, now you should see the screen properly.
Yeah.
Is it?
Yep.
Okay.
Yes.
So well, thank you for the invitation to this series. In generally speaking, in this series, we the subject is let's say the relationship between humans and machine, one of the main subjects. So we basically want to enter this subject as well from a different perspective. First of all, from my perspective, and it is the perspective of history writing. So basically the major question I'm going to approach, and Grégoire is going then to deepen, is about so what it means to have, let's say, a machine, in this case a computer, as a support while doing history writing. So, and the examples you will see are from a project on history of cosmology. I will show a few steps and then bring the word to give the word to Grégoire. So what you're going to see now, it's from a project, the Sphere, Knowledge System Evolution and the Shared Scientific Identity of Europe. This project is also part, though with a little different name, of BIFOLD. BIFOLD is of over-institutional research organization founded by the Ministry of Research and Education, to which many research groups belong, among them, so this project from the Max Planck Institute, but also other research group to one other research group at the Faculty 4 of the TU in Berlin, to which Grégoire belongs. So, and we work together. Grégoire is an expert of machine learning from a theoretical point of view, even, and I am a historian of science. So how does these all work together? In this project, we analyze historical sources and we try to figure out how scientific knowledge evolved and was transformed during the early modern period. And in a sense, how this knowledge also became more and more homogeneous and standardized. And that's why we are speaking about scientific identity in Europe. We collected a corpus of historical sources. These are 360 different editions of textbooks used at the European universities to introduce the students to astronomy and cosmology. So basically in the first year of the faculties, of the studies in the faculties of liberal arts in Europe. So the first, these are printed editions. The first was printed in 1472, the last in 1650. So you see, we are speaking about a long durée historical project because it's about 180 years. You see here the geotemporal distribution of the production of these textbooks, so the printing of these textbooks. And if you consider an average, which is quite realistic, of about 1,000 copies for each edition, so then it means we are speaking here about something like 350, 360,000 books that were circulating in Europe and were used by students all over Europe to study, to learn, and to make their examinations in astronomy and cosmology. These treatises are introductions to geocentric cosmology of the time. So now, if you want to analyze these treatises, so which in total make 74,000 pages, then of course you have different possibilities. You can try to read all of them, annotate all of them, work in a very standard way, or try to figure out how you can use the computer, let's say, in a very general sense, to help yourself. So first of all, you have to decide which kind of data you want to extract from these books for according to your research questions. And so this is what we call knowledge atoms. The knowledge atoms are those data that for us are representative for the knowledge, for the kind of scientific knowledge that is displayed in these treatises. And so you have many possibilities depending on what you are looking for. If you are a historian of books or from a material perspective, then maybe your data are also concerned with the thickness or quality of paper or of ink. If you are a historian of science, let's say you tendentially first go to the texts, to the illustration, and to the tables. And this is what I'm going to show to you. These are the three knowledge atoms I want to show to you how we deal with. So the first one is the text parts. So we figure out a way to bring a sort of autopsy of these books. So we divide these books into text parts. So we dissolve them, we atomize these books, a little bit like when a medieval commentator prepared a lecture for the class for teaching. So it was, you know, atomizing the text and then inserting explanations. We don't really insert explanations, but we just atomize the text according to what we call text parts, which is something that has a beginning and an end. Very clearly in the book. So this could be a paratext, it could be the fundamental treatise of Sacrobosco, Tractatus de Sfera, which is at the base of our studies. But there are many other little texts that are added to the treatise, or that are added as a commentary or as a paraphrases, and many other ways. So we have a taxonomy. We distinguish among original texts, commentaries on original text, translations. We also have the category fragments, and so and all possible combinations are there. You can have a fragment of a commentary that repeats in another text. You can have different commentaries on the same text. You can have different translations of the same text or commentary on a translation. So all possibilities, and you can immediately imagine how complex all this can become. We obviously developed also a repository, and is a graph database, quite complex, with an ontology in CA.CRM to keep all this knowledge that we are extracting in a sort of graph, in a sort of network already from the very beginning. So here I show to you a little bit how it works. This is a typical entry for one of these treatises. This is a big anthology from 1531. Usually the books, our treatises are a little bit shorter. So this is the long title. We have all the metadata, obviously. So we have the authors as they appear in the title page. Then we went into the books, we discovered much more content, and we discovered specific chapters or specific texts that are not declared in the title page, and so we call them the authors of these text parts that are distinguished from the declared authors. So in this case, we have 26 text parts. So here is a poetry, an epigram, oratio on astrology, and commentaries. Here a commentary of Prosdocimo de Beldomandi on the Tractatus of Sacrobosco. And one important characteristic of all this is that these parts tend to reoccur. So we have about 500 parts, and around the half of them reoccur over time and in the treatises all over Europe. Here you see, for instance, if I go here, this is a commentary by Jacques Lefebvre d'Etaples, and you can see that this commentary is contained in a series of about 15 treatises published between 1494 and 1534, I think, or 38, and in different parts of Europe, of course. So basically, we look at the circulation of these text parts, which are representative for the knowledge. And if you go up for all text parts, and some of them repeat only once, some of them repeat up to 90 times, so you immediately understand that the graph of distribution of knowledge and evolution of knowledge as we want to analyze it becomes pretty complex. In addition, we have several thousands of reoccurrences. And in addition, we have this ontology that taxonomy, I'm sorry, that we develop, commentaries, original text, fragments, translations, and so on. This is when you then want to get all this data and have an overview of all of them and to try to understand their behavior of this data, then of course a database is no more sufficient, and even a big piece of paper where you can write everything is not sufficient. So, but then we go to more mathematical means, and we develop all these graphs that represent. In each of these graphs, you see the books that are linked to each other according to several hypotheses that we developed. So for instance, whether they contain the same translation or different translations of the same commentary. And so they are linked together. Each graph has a different meaning. Why are we doing this? Because we want to discover which kind of mechanisms were active in order to transform this knowledge and in order to make this knowledge more and more standardized, more and more homogeneous. So basically, for instance, what we found out, and this we found out is that at a certain point there was a constellation, a combination of these text parts that became a sort of model. It became hegemonic, and it was imitated everywhere. So this is a typical mechanism that we want to discover, and we wanted to know, so how this new combination of text parts look like. It's because people started commenting more or stopped commenting, or because people began translating this text from Latin into a local tongue. So what is actually the relevant aspect in the knowledge production in order to gain hegemony for a certain model of a treatise? What it turned out is these two multi-layer networks that we have analyzed have shown to us that indeed there was an hegemonic combination, or a combination of text parts, a sort of model book that emerged around the 30s of the 16th century, and this was conceived, designed, and produced in Wittenberg. So after the Protestant Reformation. And this became really a model that was imitated everywhere behind the confessional boundaries and borders. So this is the kind of studies that we are doing, and we can analyze all this data by means of these mathematical means. So this is for what we have done for the text parts. These two multi-layer networks are representative for two publications, one in 2019 and one in 2020. So very recent, a few months ago, that was then published in Scientific Reports, Nature. And so if you are interested, then I can send to you the DOIs to download the PDF. So as you see, so this is the first example. And in this case, we have databases like graph databases, and this is basically, we applied method from the physics of complex system to analyze this data. So until now, no machine learning, by the way. But if we go to the next knowledge atoms, the illustrations, then we start looking at a little bit more what machine learning can do for us. We consider illustrations obviously as a different knowledge carrier. It is ontologically different from text. It can enrich the text, describe the text, but also criticize the text. If you think, for instance, of the authority that usually was given to the text, it was much more difficult for a commentator to change the text, so to speak, or write a new text. It was easier to comment on it. So there was this authority, but sometimes through the images, we have noticed that many criticisms were actually added without changing the original text from the medieval period, for instance, or even from the ancient period, because in these books you find text parts from several epochs, and so from ancient epoch, from the Islamic age science translated into Latin, and then from the late medieval period, plus early modern text. So we decided to look at the behavior of the images of the illustration to figure out how they evolve, how the visual apparatus evolves over time. And in this case, so the first thing you need to do is to find all these images. Now, I wrote there we have about 20,000 in our corpus, but how do we find them? Actually, we started we started segmenting and capturing them manually because we were not yet in the project together with Grégoire. Then we entered that project and we learned a lot. And so this is a typical way. So consider how you could work if you have a big corpus. So you dismantle your books into single pages. So, oh, sorry, I need to get it started. This is a little movie. It should work. Does not. Yes. So, and you have pages of the book, and the algorithm that was developed by Jochen Büttner in this case finds all the pages that contain images automatically. So this is classifying, and then segmented them. So it shows you where the images are and how they, so how big they are and so far and so on. So you see it works really very well. So you can go through 74,000 pages in this way in a few hours, and you find these exceptional results. But if you look at the top left, for instance, you see that this is not an image. This is a title. But if you could read the red bar, you could see that there is a value, a probability value, whether this is an image or not. And there the value is low. So it means that you, as an operator, you, me, Grégoire, we decide when this value is enough, in the sense that we decide a cutoff. Over this value, everything is an image. Under this value, we might have mistakes, but there might be also images as well. So it means we are starting working probabilistically. So we are starting deciding that we will not be able to really capture all the images, but we capture a certain percentage of them. And this is given by the algorithm, not by us. And we can only decide the cutoff. So this is already a very different way of, a different method to do history. Because in a sense, we want to do something like a long durée project, but with the depth of a case study. So looking at all the sources, 360 books, so which you would never do in a normal case studies. On the other, to do so, we need to use means and tools and technologies and develop them themselves for us that do not allow us to keep working a deterministic way or in the typical standard way. So we need to accept to have a trade-off between the two aspects. But in this way, you can have 360 books, but you can also have 36,000 books, and it wouldn't change that much. You need a good computer or a computer facility, but the algorithm wouldn't change. So this is the first point I would like to put to your attention, but we will have more of this. Here are the images, and so we have a little taxonomy inserted manually, whether these are scientific illustration, initials, decorations, frontispieces, title pages, and we also have printer marks, which I forgot to write here, sorry. Once you have all these images, so all this data, the first thing you do when you have data is to explore them, because you search for patterns like everyone would do in data science. You search for specific or peculiarities or something that can eventually bring you to a more specific research question. So for this, you use visualizations. For instance, is one of the many methods, but you can have more mathematical or arithmetical methods. And here in this case, we just wanted to visualize the temporal behavior of all our illustrations that we were able to extract. And what turned out, for instance, is that we discovered that after 1530, the number of illustrations increased a lot in these books. So there was first the Protestant Reformation, following the so-called Immatriculationsloch, so the number of students at the university dropped down for a few years. And then we have, again, a radical increase of production of textbooks. The number of students increased a lot. But what is different in these textbooks, even if they are on the same subject and commenting on the same medieval books, is that they are much more illustrated than they were before. So you see, we discovered something, but actually by exploring the data, the behavior of the data, we actually defined a research question instead of answering a research question. So this is also another way to be supported by these kind of technologies. Now, what do we do? When you work with data or when you work with any other thing, even in a standard way without data, with your own annotations while you're reading a book or consulting a manuscript, you basically always use a philological approach. So we have classical philology, we have many ways of working. I mean, we always use a philology, whether we are conscious about that or not. When you work with data and you have an approach from the point of view of computer vision and machine learning, your philology basically reduces, although reducing here does not simplify things, to, for instance, the concepts of sameness and similarity. So what you have to decline everything in this way in order to build up algorithms that are able to find similar or identical or different things according to the way you can interpret these terms. For instance, if I'm able to find two identical, really identical images, I could infer that they are produced by using the same woodblock. So it means maybe if I have two printers in the back of these two books, then I can say, okay, one printer lent or sold the woodblock to the other. So this is an information concerning economy of the books. But if I have also all the images similar to each other, if even they are not really identical, but just similar, and I match this data with their scientific meaning, you can have two images with the same scientific meaning, but completely different, then I can figure out how to, I have the data enough to study how the visual language in science, in astronomy in this case, actually evolved over time, which is our goal. Now, and a little example. Here, for instance, you see four images on the right. These images are all representative. Each of them is representative for a group of other illustrations which are identical. These four groups are then put together as types of representation because they are very similar to each other and because they are there to explain certain aspects related to the phenomenon of lunar eclipses. But we also have completely different images that explain the same phenomenon, and they are clustered, they are grouped in different ways. So in this way, if we put then all this data together, we match them with our metadata of the books, we can find out where, for a certain explanation, a new visual representation was created, whether this was successful or not. For instance, it reappears in other books all over Europe, or whether there were experiments, for instance, somebody who made something different and nobody cared about that, or, and also see whether traditional ways of representing certain scientific knowledge actually got into oblivion in this way, and where and when. And so this is the kind of studies we also are doing. But to do so, obviously, we need to cluster and to group all these images according to these certain levels of similarities that I have shown to you. But this is not very easy if you have 20,000 images or 2 million images. And so for this, then you go back to machine learning with all what it means. So here is the result of an algorithm that clusters automatically the images according to the criterion of similarity. So they don't have to be identical, or actually they want it to be identical, but let's say they are similar to each other. So you see that it works pretty well, but if you look a little bit more focused, you immediately discover that there are mistakes, so to speak. There are images that are not really identical to each other, or not even similar to each other, and they are by mistake in these clusters. So here there are many technical reasons why this happens, but this here is not the point. The point is, when do you decide that a cluster like this is reliable for your study? So basically, this is a decision that you take. You go through and you say, okay, so these clusters are good enough, and I stop here. You could then clean them manually if you want, but if you have 2 million images, you can't. So also in this case, the algorithm brings you to a certain level, and over that level, maybe you don't go because it would require a lot of human resources to train, or because it's technically impossible, or because it's just not needed. So the question is, when is it reliable? And the point is that the more data you have, the more a cluster that has mistakes like this becomes nevertheless reliable for you. So basically, this technology not only brings you away from a sort of deterministic approach to the source analysis, typical for historians, but it also brings you to the necessity, I would say, to analyze an increasing number of historical sources, to enter into a sort of continuum in the long durée projects, long durée reconstructions, where you are obliged to take really into consideration a lot of sources, also in order to make your data more reliable. Now I move to the next knowledge atoms tables. We have also here, we have classified and found the pages where there are tables. If we speak about only numerical tables, we have about over 11,000. So tables in these kind of books look like this, for instance. So you can imagine whether you can work or not manually on them. Also in this case, our goal is to connect the books, to create new graphs where we can see which book contains for the first time a specific table, which other books, which other printers, authors have republished this table or expanded this table. So in this case, we have eventually the same tables or the similar tables. And these are computational tables. At the same time, they speak about the use of math or the increasing use of mathematics in this book. So this is nothing less the process of mathematization of science. But how can you actually analyze 11,000 computational astronomic tables like this always in completely different, printed in completely different layout? So this is a very, very big challenge. And for this, Marcus, we indeed go into the issue of deep convolutional networks, because this is something that we are doing with Grégoire, Oliver, Eberle, and Jochen, and we are working on this. We have been working on this since quite a while, and this is a very sophisticated technology that really brings the historians quite far away from the typical way of working. But that exactly in the last weeks, we were able to achieve very good and convincing results. And at this point, I give the word to Grégoire, who then will tell you a little bit more about this network, how this network works, also from the point of view, let's say, from a more mathematical point of view, which is a good example to show how historians then have to work. So they have to work also on that level and try to understand how really these networks, the nature of these networks. So I go to Grégoire, which means I stop here because Grégoire wants to share his screen as well.
Okay, so I think you can see my screen and probably hear me, I hope.
Yes.
So yeah, so I will just make a few, present a few slides that take a little step back and look a bit more in what is machine learning and how do we formalize the problem of machine learning. And basically, this is like a typical formula that you would have in machine learning, which is composed of several terms. And you have basically X, which is your input data. So for example, your image. Then you have a function F, which can be anything. So it can be a deep convolutional neural network. And usually this function f is actually hard-coded. So for example, it is a neural network with connections that are hard-coded to form layers and then to form a whole network. And what we learn is not the function f, is some parameter. And this parameter, for example, can be all the connections that are connecting different neurons of the network. So that's for the structure of the model. And how do we train it? Basically, we have some ground truth, which is denoted by Ti in this slide. And then we would like to make the ground truth and the prediction match. And therefore, we compute the difference between the two. And then we try to minimize over the parameter of the model. And we don't compute the difference only for a single example, because it would be easy to train a network that just match one example. We do it over a sum of many examples. And this can be hundreds of examples, or if we have a lot of data, up to millions of data points. And this is an example, how would you train a horse detector? If you have like horse in images, and then basically you have some input, and then some ground truth. And the ground truth is collected from the human, and then you would just like acquire this data set before performing the minimization. The minimization over this parameter theta can be like implemented by different techniques, and there are a lot of techniques to do that in machine learning. A popular one is called gradient descent, and that's basically for classification. But now, as Matteo was mentioning in the first part of the talk, I know maybe one more thing. Why do we want machine learning? Mostly it's because we want to be able to automate these different tasks. So if we would have like a large data set of millions of images, we would like to predict them, then we would need to basically collect all the labels manually. And this is actually might be sufficient for thousands of examples if we have a lot of resources, tens of thousands of examples, but it will not work for millions or billions of images. So the idea is to use a small subset of the data that we have currently, and then collect ground truth. So basically ask human to provide label to these images. And then after that, once you have collected sufficient data, we would like to train a neural network. So it will take some time. But once we have it, then we can very quickly predict the images for every other example that we haven't seen yet. And ultimately, if the network has been trained and generalized as well, then you will be able to save a lot of time compared to do the whole process manually. So that's the reason why we want machine learning, is really to automate these tedious tasks of labeling. So now, as Matteo was mentioning before, we don't want not to only perform classification, but we also would like to be able to find which documents or which images are similar. And this is the same equation as I've shown before, but just rewritten in a different way that supports similarity learning. And you have basically now not a single X, but you have two of them. And these are basically your pairs of example, where you want to predict whether they are similar or not. So basically we can pass them, each of them, to a neural network, and then you apply a dot product, and this is basically the similarity prediction of your neural network, and then you compare it to some Sij, the right-hand term, and you would like this to be small, and Sij is the ground truth. So how do we collect the ground truth in that scenario? So back to the tables now. We need to have an expert that look at these two tables and say whether these tables are similar or not. And in the best case, we would even want the expert to tell us whether these tables are the same or not. And getting this information actually is a very time-consuming process, because it would require to meticulously inspect the two tables. And that's something that takes a lot of time if you want to do it manually. So trying to solve this optimization problem and would require a lot of labels, and that's not really possible. So what we have done in our work is to not train the whole similarity model end-to-end, but instead to use a bottom-up approach. And the idea will be to first try to detect small component of this table, for example, digits, and then add layers one after the other to compose and to build progressively the similarity metric. So this is how our machine learning pipeline looks like for comparing tables. So first you have some table, and here you just have a small fragment of the table, and you will carry out the simple task of just predicting individual digits in this table. And if you do that, you can train a convolutional neural network that outputs blobs at the location of each digit. So with this network that you can train, and for this you just need annotation of a few individual digits, maybe 100 or 1,000 of them, then you can, for every table, predict 9 or 10 feature maps that have blobs at the location of the corresponding digits. So that's our very first layer that we train, and that's the only machine learning part, actually. Then all we can do is to hard code layers to build more complex representations. And what you see, a second layer, is this bag of features. And here the idea is that we say now we don't want to only have a detection of individual digits, because it's not very informative, but we want to be able to detect numbers. And what we can do, we can take these feature maps, try to make them coincide by shifting them by a few pixels, and then multiply them. And if we multiply this feature map, we can basically produce blobs only when certain numbers match. So out of these 10 feature maps, we can compute hundreds of 100 feature map that detect these bigrams, or these numbers between 0 and 99. And finally, you can say, okay, maybe information about number is sufficient. I don't need the special information to at least for the purpose of my similarity task. And we can sum this feature map in the pixel space to arrive at a histogram that basically counts the number of times you see a certain number in the input table. So now that we have this network, so again, the first layer was trained, the rest was hard-coded. Now we have this representation as a histogram in the top layer, and we can compute this dot product to verify if these two tables are similar. So with this machine learning approach, now we can basically take a large data set of tables and project them into the neural network, map them to the neural network to arrive to be able to basically compute a similarity score for every pair of table. And this is something that wouldn't be possible by just manual annotation, because there are too many of these pairs of tables. But now we can have these numbers, and the network now, we can take these similarity scores and run, for example, some clustering algorithm and look what we have found, whether these clusters are actually groups of tables that are really the same, or that are exactly the same. And this gives us a way of inspecting this large collection of tables. So now there is one aspect of machine learning which is important, is that sometimes we don't know a priori how the machine learning model exactly decides. And this is another neural network that was trained to predict images. And this network usually performs very well. And sometimes there are some very surprising results. So for example, here we see two images that are different. I mean, this is not the same, but they happen to have some very similar content, but they have some rotation. And we find that, interestingly, this network assigns a lot of similarity to these two images. And from this simple observation, we might jump to the conclusion that the network has actually learned some kind of rotation invariance. But here we have a tool which is Explainable AI, which lets us find out what is the true reason why a prediction has been performed in a certain way. And if we apply this, basically it gives us a connection, basically, that tells us what are the pairs of pixels that have been supporting this decision. And here what we find out, for example, is that it is not the rotation that was detected. So in fact, the sun on the two images is not matched. It was something at the very center of the image that happened to have not moved. So this was a rather unlikely case, but this is something that we would like to avoid when training a machine learning model, because then we don't know what will be its actual generalization behavior. So it's important after having trained a model to also look at what it has learned using explainable machine learning. Just to recap the 3 points I've made. So machine learning is important because it can automate repetitive tasks, but you need for that a human that collects some ground truths. And sometimes, and especially in the context of tables, ground truth is hard to acquire. So here we need to use, we have proposed to use a bottom-up approach where we train some part, but the rest is hard-coded. And then finally, what we need to do is to verify that the model is right for the wrong reason, right for the right reason and for the wrong reasons. And for this, we can use Explainable AI to find this out. So I think I will let Matteo now give a few final words. So I unshare my screen, so I think you can continue.
Yeah, well, I don't have any slide anymore. I mean, just a few words. I think what is important here to realize is that, in a sense, when you use machine learning, it's not that you are capitulating as a historian, but you are bringing your knowledge not only in the usual way. You need all the knowledge and all the standard methods, nevertheless, but you are also bringing it into what is called here the training set, the ground truth. You need to create a ground truth. And when you, the architecture of the algorithm and the ground truth are the two aspects that you as a historian need to know and to figure out what is relevant for your research question. And this, so you transfer your knowledge in this way into, you embed it into the machine in a way, which however is not working deterministically. And if the task is really so complex that you can't do that, then you can go to the other solution, to the so-called lazy solution, where you try to figure out how the machine can learn it for itself, and like in the case of the tables that we had. So obviously, you see that the great advantage here is the total independence. In the last case, is the total independence from layout, from any kind of graphic, and still you are working. You're working in the frame of computer vision. So it means that the heterogeneity that historical sources bring to you is something that can be faced in this way, and it is, by the way, what also makes history quite interesting from the point of view of those who develop, or from a theoretical point of view, machine learning technique. And then there is this last point where you enter almost in a dialogue with the machine, where the machine is able to find something you consider right. And but then nevertheless, it might be the case that the machine has followed a completely different argument or completely different logic, so to speak, to get to that conclusion, which means then that there is explainable AI. And when you go with this approach, you really enter in a dialogue basically with the machine in order to understand and to compare your own arguments with those developed by the algorithm. So this is I think the interesting challenge, and I think we have said a little bit how history could change if we go in this direction. And I stop here, and thank you very much for the attention.
Yes, yeah, thank you. That was quite, at least for me, quite overwhelming, especially the second part. The math was way beyond my head, I have to confess. But hopefully not. Hopefully I'm the exception here. Oh yeah, that's. I'm sure there are questions. Who would like to say something, or maybe I don't know, add something perhaps, or I don't know, anything. Matteo needs more light.
Yes.
That's a good sign. It's, yeah, Julia.
Yeah, thank you very much, Matteo and Grégoire. I have a very silly question, but I wanted to ask it anyway. I mean, if I understand you correctly, you are basically developing a a software.
Pardon again, sorry, I missed one word in the middle.
Yeah. If I understand correctly your presentation, you are developing a software as well. I mean, in the sense, the algorithms that you are using now will then be, they could also be used to study something else, like, I don't know, diagrams in the mathematical manuscript of Euclides.
Yes.
Or not, or it's
yes.
just specific.
Yes. No. The whole idea in the background is also related to the question: what can we develop on the basis of these historical sources, which makes sense to me, to my project, but that can be helpful in general. And actually, we were having this discussion a few days ago. Certainly everything that you have seen can be easily used in any similar projects. For instance, your example, I don't know, mathematical diagrams. So what you need to do is, of course, to take the code, install, and eventually train it yourself further. You know, because if you use different materials, now we didn't work with horses, or I don't know, with other things. So if you really want to with fishes, then you need to retrain in most of the case. So as long as you remain, let's say, quite close to this frame, it is enough for this kind of technologies and application. It is enough to have a further training. You know, just you keep training, you perfectionate, so to speak, the training. But Grégoire can also go 1 second into this. Different is when you take a step back and you look at it on a more abstract level. More abstract level in the way Grégoire usually look at these things, and not we as historians. So what is this algorithm able to do? Which kind of other material can we analyze? For instance, looking at the distribution of digits. Imagine if instead of digits, you are looking at the distribution of something completely different, but nevertheless with the same visual approach that we have here. If you are able to think with a bit of fantasy, or because there are a lot of people doing machine learning now, and you know the projects and you are informed, if you're able to think of something similar, then this basic fundamental structure of the code can be reapplied. In that case, obviously, just a little bit of training wouldn't be enough. Maybe you have to adapt other things on a more profound level. But this, I stop here, because then I enter into a field where I feel unsure. But maybe Grégoire can add on these possibilities of reusing this kind of technology.
So you wanted to reuse this. So I'm not sure I understood the question. So you want to reuse this technology for different a different type of problem.
Exactly.
Yeah, I was very interested, for example, if what you are developing, your system could be retrained, for example, to recognize diagram in manuscripts from about Euclid, for example, ancient mathematics. But also I was very, very interested actually in the visual recognition of the titles. If this is a system that could, for example, be retrained to recognize titles in PNACs, for example, in manuscripts.
Yeah. So I think the reuse of part of the machine learning model is actually something quite commonly studied in machine learning, and this is called sometimes multitask learning or transfer learning. And so there are all the mathematical tools to do that. The question is that transfer learning works if there is some kind of common subspace between the two methods. And I think, like, for example, for the problem of tables, it's very specific. So one thing that we have tried first was to train just a standard take a standard classifier for computer vision and just transfer it to tables, and it was working at some tasks, for example, detecting table versus not table, but we could not use it to predict table similarity because it didn't have the right features for that. We had to develop specific structures. So in general, yes, that's possible, but yeah, it's maybe, especially in the context of digital humanities, I'm not sure how likely it is that the task will actually share the same types of features.
Thank you very, very much.
Okay, anybody else? Yes, Marie, I don't know your full name, but Marie must suffice. We don't hear you, unfortunately.
We don't hear you. We don't hear you.
I just
Yeah.
Ah.
I unmuted myself. Can you hear me now?
Yes.
Okay. Matteo, I think we met before.
Yes, hi Marie. Yes, I think this is the third time.
Yeah, it's really interesting. I was just wondering whether with the table recognition project, you got to the point where you could successfully compare the numbers, or was it just about identifying similarity of the tables in terms of the visual aspect?
Well, we are able to say when two tables contain the same number, basically. So
okay,
up to a certain degree. But maybe this is a good question that can be answered in detail, but certainly much better by Grégoire than by myself. So the way this really works, it's not just, you don't have to think in terms of OCR, so to speak. This is not the point. Maybe Grégoire.
So basically, in tables, it's very difficult to be able to have the structures to recognize whether two tables have it's very difficult to predict whether two tables are exactly the same and basically contain the same structure. Mm-hmm. So we took the approach to say, okay, we have a lot of numbers, so maybe we don't need to care so much about whether these numbers are in the same order. We just kind of atomize the table into a set of numbers. And then because there are a lot of numbers, that's statistically sufficient to predict similarity. It's really just taking the table, view it as a collection of numbers, and then detect this number using machine learning, right? Like some kind of digit recognition, and then recombine them by computing some product between the two vector of numbers we get between the two tables.
I think the reason why I was interested is because you said you were combining hard-coded elements with your machine learning techniques, right? Mm-hmm. And so I guess some random thought I had was that there must have been some predictability as to the tables in terms of like how many columns they have, you know, like if it's something, if it's related to months, or if it's related to days in a month, or what have you, not another typical feature of an astronomical book, then maybe there is like a hard-coded prediction one can build in. I guess I was just interested if that was.
Yeah, so definitely there is some complex structure that could potentially be used, but as a starting point, we found out that it's sufficient to give it on some of this structure, because sometimes we don't know exactly whether something has a specific meaning, but we can recover it from the number itself. And then just recompose and use the fact that there are sufficiently many numbers in the table to get some statistical confidence about our similarity prediction.
Okay.
But yes, I mean, you could create like some examples where you take the table, you completely shuffle the numbers, you will get the same similarity score with our model. But that would not be the same table anymore because it would have changed the meaning of the different relation.
Right.
But it turns out that such shuffled tables are not very likely. So we don't run so much into this problem.
Right. That makes a lot of sense. Thank you.
Yeah.
Okay, thanks. So the next question is Konstantin Schulz.
Yes, thank you. So I have a question about sample efficiency. So you've shown us how some of the images that appear very frequently and repeatedly, how you can compute the similarity and cluster them. But in the humanities, people are often interested in the infrequent phenomena that might occur only once or twice and then disappear, but they're still interesting. So how well does the model perform in those cases?
Well, it's actually quite easy. The model doesn't have any preference for any of the two cases. It clusters, and let's say in the best of the world, it clusters, and you have huge cluster when you have a lot of images similar to each other. And then if there is one image which is unique, then this is a cluster built by one image, so to speak. And then it is up to you. If you are interested in looking at the let's say single cases, then you look at those clusters which are the smallest ones. For instance, all those constituted by one image or two images. So in this sense, the clustering process is totally neutral. What you do, what you are interested in, it's you, and you can use the data as you prefer. There is, however, one point which I didn't say, but when you cluster in this way, you basically have to say in advance how many clusters you want to have. So, and this, of course, is a top-down approach that does not respect the empirical data, because you don't know how many clusters you really have in yourself. So you can say, I want to have 1,000 clusters, or I want to have 2,000 clusters. And then what you need to do is to go to the clusters and analyze them and see whether they are, homogeneous or totally mixed, especially the biggest ones, and so on and so on. So, and then accordingly, you have to retest. So there is, let's say a little bit of, it's quite an artisanal experience sometimes, I have to say, when you work with these algorithms, because it's always a back and forth. And then you never know, because maybe you have introduced other biases, or there are other reasons why the cluster are not clean enough, or the kind of thing. So there is a lot of testing around. But basically, our approach is not to look at the biggest or at the smallest cluster. So we want to have all of them, especially, as I said, because for me, it is not only important to see, the super successful innovation, the image that was reproduced other 1,000 times, but also to see where there have been experimental approaches to visualize science that maybe haven't had any success, at least in the first phase, or for a certain temporal phase, and then later on, yes again, and then figuring out why this happened, why there was this so-called sleeping beauty that then becomes successful later. So all these aspects. So I can't exclude anything, basically, because but the exploration is really neutral. So we don't know what's coming up. Then there are special characteristics of the algorithm themselves. Maybe I don't know whether Grégoire wants to add something to this, but our approach is not to find the most successful ones, is to find everything.
I can just add something maybe more from the machine learning side. So yes, it's right that there are, in machine learning or in data distribution, there are always very frequent data points and more difficult ones that are more rare. Typically, we have that in image classification, where we have plenty of images of cats, but very few images of some very specific objects. And therefore, it's with pretty much any simple algorithm we can recognize cats, but some of these more rare classes are much harder to recognize. So in that case, it's important to be able to reuse the features across different classes, and specifically transfer learning. And what we have used in our approach basically is to actually not train to detect features on these images. It's just to reuse an existing pipeline which has been trained on a lot of images, like natural images. So a state-of-the-art neural network for computer vision. And then we have basically used all these parameters, and it gives us already a lot of high-level features to build our clustering algorithm on. So that's how we have addressed this problem of rare tables in the context of rare example in the context of images. And for tables here, we have used a slightly different approach, is to just focus on learning the digits recognition. And here we assume that all the tables are composed of digits, even if they are very uncommon, right? So since we only train that, we have a good digit recognizer, and then we add this hard-coded example, these hard-coded layers on top of that. And then we don't have like the model performs equally well on frequent table and on rare tables. And then you can run your clustering algorithm, And yeah, basically, if there are two rare tables that are the same, they have equal likelihood to end up in the same cluster than if these two tables were occurring very frequently.
Thank you.
Okay. Any more questions? If not, I would like to ask Matteo about the knowledge atom, the idea of knowledge atoms, which I find really productive, especially when looking at knowledge traditions over a very long time. And of course, you looked at a rather, at least from my point of view, a rather homogeneous period of astronomy, perhaps, where you would expect, if you look at all these textbooks, to find always the same, whatever you would expect to find in most of the texts, all these knowledge atoms and in a similar way. But I guess if we looked at ancient Greek astronomy or Mesopotamian astronomy, we would certainly find other less, I believe, less knowledge atoms and other kinds, and some die out and some become more and more. And I guess that in, I don't know, 19th century astronomy textbooks or modern ones, we again have more different kinds of knowledge atoms and completely different forms. So my question would be, if you think it would be useful to think about the long time development of knowledge atoms in a given field. I'm not quite sure, but it sounds, to me at least, it sounds like a productive approach.
Well, I mean, the question is on one side easy, on the other super difficult. And so let's say now, historically and empirically speaking, what we have now concerns all the history of astronomy. In truth, I have already studies and collections that move outside the history of astronomy of this period, and I obviously used historical categories in order not to create any break and to make all my data totally useless. So, and the classical category you would use in this sense, as I'm speaking about textbooks and Faculty of Liberal Arts, is the category of the quadrivium. You know, so I move from astronomy to Euclid elements to Boethius, the Musica. So all these kind of texts that were used by the same students in the same time, and you will find a lot of similarities there. And so there is the way to expand in this direction. Temporally speaking, the data can be, at least those in astronomy, can be used perfectly, also going back to basically the foundation of the university to the 13th, until the 13th century. So we have, you certainly have, between the 30th and the 17th century, I don't see any specific problem in reusing exactly the same atoms. Obviously, you have to keep expanding and so. What happens, however, if we take now your example, going back to antiquity, or going back to Islamic age science, or going further to, I don't know, 19th century astronomy, for instance. Well, this is something that has to be somehow done in order to answer this question. What I can see is that in any process of scaling up of all these projects, it's like you make a step back and you see them from a more distant vision. So it means that the depth that I have now, somebody has the micro, and maybe could you, I hear myself.
Yeah, no, we understand you. Everything's
okay. So the point is that you have to make like a step back. You have a more distant reading. When you make a more distant reading, certainly the knowledge atoms you can collect and the knowledge atoms that become interesting for the kind of questions you can develop by that distance are slightly different. And so this is exactly the art of the story. So to find those that allows you to recognize this continuity, and then you can go back and forth. The distance can change all the time according to the depth in the specific epoch. I have to admit, this project is in this sense well chosen, because yeah, as you say, the knowledge displayed in these books is, in a sense, let's say, quite homogeneous in itself because it's geocentric cosmology. But you shouldn't believe you shouldn't believe that it is all the same. There are huge debates within the geocentric cosmology, and for everything, for every kind of further movement in the stars, it was observed, explanations, and then consider all the development of cosmography and geography that takes place in this period, and it becomes part of this book. So there are a lot of changes, but for instance, what is missing there is what you would expect to find there, especially as a historian of astronomy, Copernicus. Now, the Copernican revolution. The history of astronomy has been always the Copernican revolution. There is nothing about the Copernican revolution till 1650. These books are no more used, and there is no Copernicus. So, they were teaching geocentric cosmology for other 80 years with no difference in this sense, concerning Copernicus or Tycho Brahe, Galileo, whoever you want, and nothing. So the question is, if I take now the Copernican works into consideration, into my corpus, would it work, for instance, in the same way? Well, I made some tests, manual tests, also with some colleagues in the Netherlands. So we took, Kepler, especially, and so on. For instance, we looked at the images. So the visual apparatus, as long as we are speaking about the same phenomena, does not change. So the continuity is way deeper and way more relevant than what you would expect. So basically, nothing speaks about revolution. So, this is what we got. So in this sense, I'm quite confident I would find a solution, but for a really long duration history, like for 600 years, this has to be first done, and then we can answer. So how it really is. Yeah.
Okay, thanks. Yeah. Very interesting tool. Any more questions? Julia, do you have anything to add?
No, thanks. I mean, not a question. I just wanted to say a big thanks for this fantastic presentation.
Yeah, me too. Thank you very much.
Thank you.
Okay, when's the next lecture of the prostate?
Yeah, the next lecture should have been on the 15th, meaning next Monday. But unfortunately, Serafina Cuomo has asked us to postpone it to the 15th of March. We already updated it on the program, and we will send off a couple of emails during the weekend, so to make sure that people will know that.
Okay.
Meaning the next lecture will be then Nora Gotze, also machine learning in digital humanities, chaired by Roland Baumgarten. And I think the date is the 18th of February, but I'm not sure about it. Anyway, at some point next week, but it is on the program online.
Okay. So
yeah.
Thanks again for this very interesting and partly confusing, but somehow